Hey guys, my name is Mohan,
And I'm Adriana.
and today we're going to talk about next year's AP Chemistry Learning Objective 5.1.
And what this entails is learning about the connections between potential energy and the distance between atoms, as well as the bond order and the polarity.
Alright, so hope you like this presentation.
To start off, we're going to be talking about potential energy.
So what is potential energy?
Potential energy is just the ability to do work.
So AD, is it just mechanical systems that can have potential energy, or can chemical systems as well?
Well, actually, chemical systems can also have potential energy, and it's usually stored in atomic bonds.
Oh, that's interesting. So you're saying that atoms and bonds can have potential energy as well?
Yeah, the bonds between atoms can be released by various chemical reactions.
So now let's talk about potential energy and the distance between atoms. So in atoms, the potential energy is always dependent on the distance between two atoms.
So if I'm at a very far distance from Mohan, way far away, then there's a very little attractive force between the two of us because there's so much space in between us. But if we're too close together, our protons repel each other. So there's a very strong repulsive force.
So basically, if two atoms are too close together, they'll repel a lot, and when they're too far apart, they might come together. So they find an equilibrium point where they come to be bonded.
As Mohan talked about before, the balance between the repulsion and the attraction of these atoms is called the equilibrium bond length.
When we look at atoms and their distance and their potential energy, we look at something called the Morse curve. Now the Morse curve shows us the potential energy based on the distance between two atoms. When they're far apart, there's not too much potential energy, and when they're too close together, there's a lot of potential energy. Atoms tend to balance out when the potential energy is the least, and that's the minimum on the Morse curve. The stronger a bond is and the closer together two atoms are, the higher the potential energy. So when the attractive and repulsive forces balance out, potential energy is at the least, and it's the minimum on the Morse curve.
Here we have two people that represent atoms. On their arms, they have green tape, and this represents the electrons. On their hearts, they have pink crosses that represent the protons in the center of the atom. As you can see here, as time goes on, the electrons are attracted to the other person's proton in the center of their atom. This brings them together. However, as they get too close, the protons on either their hearts repel each other, and the two atoms move away from each other. But because of the attraction with the electrons, they find an equal distance and a medium length away, and that's the equilibrium bond length. Bonds and covalent bonds can either be single, double, or triple. The strength of the bond is inversely proportional to the amount of its potential energy. So if you have a triple bond, the potential energy is going to be very small. But if you have a single bond, the potential energy is a lot greater. The strong bonds have a lower chemical energy, and the weak bonds have a higher chemical energy.
This is because when a stronger bond is formed, or more bonds are formed between two atoms, energy is released, and every time energy is released, potential energy decreases, meaning that the stronger the bond, the less the potential energy an atom or bonded atoms possess. The more bonds there are between two molecules, the more negative the potential energy is. Take, for example, two hydrogen atoms. When we put them together and create a single bond between the two atoms, energy is released, meaning that there's less potential energy in the bonded hydrogen atoms than the single atoms themselves. This means that every time we add a bond between two atoms, we potentially lose potential energy, and potential energy actually becomes more and more negative or smaller. Take, for example, these two balls which are bonded together with rubber bands. The rubber bands represent covalent bonds. As you can see, when there is one rubber band or a single bond, the atoms can move apart much more easily and the bond is broken much more easily. As we add more and more rubber bands, you can see that the atoms become more stably bonded together, meaning that there's less potential energy. So, when the less the number of covalent bonds there are between two atoms, the higher the potential energy because they can be separated much more easily and they're less stable when they're bonded together.
Molecules tend to arrange themselves in order to reduce the potential energy. Polar molecules can line up either side by side or end to end, where the dipoles are not touching each other and therefore there's no repulsion. The end-to-end arrangement reduces the potential energy the most because the molecules are more stable this way. Here we have two polar molecules, the hydrogen fluoride and also hydrogen fluoride. Here on the fluorine side is more negative and the hydrogen side is positive because fluorine is more electronegative. When they arrange themselves, they can either arrange themselves side by side, where the positive side is attracted to the negative side, or end to end.
In summary, we've learned that chemical potential energy is stored in all atoms and bonds between them. A large distance between two atoms means that there is little attractive force, and a very small distance between atoms means that there is a very large repulsive force. When these attractive and repulsive forces balance out, you end up with an equilibrium bond length. The closer together molecules are, the higher the potential energy is as well, due to increased repulsion. That means that they're less stable. The more bonds, the less potential energy as well, because every time a covalent bond is formed, energy is released. This is demonstrated very well by the hydrogen atom and how when it bonds together to create H2, when two H's turn into H2, energy is released, making the molecule more stable, and therefore it has less potential energy. Polar molecules arrange themselves end to end in order to achieve the least potential energy as well, because they are most stable this way, when positive ends of the same molecule attract the negative ends of the other.